Okay, let's go ahead and get started. Let me first just make sure that this. Did everyone get my email that I sent out on Monday? If you did not get the email that I sent out on Monday, if you didn't read it, please read it. It was just an important announcement, or rather a reminder about the course policy on the use of previous year's problem set solutions. Just to reiterate, you are not allowed to use problem set solutions that I distributed for this class in previous years. These problem set solutions, among other things, are riddled with mistakes. And there have been several instances where it's been reasonably clear that people have been copying previous year's solutions because they copied the mistakes. Okay. And in cases where we have clear evidence that people are using last year's solutions to try and solve the problem sets, we treat that as plagiarism. The way that plagiarism is treated at this university is I'm required in instances of plagiarism to forward the issue to the Faculty of Science, and then it's out of my hands. Okay. And then there's a disciplinary procedure that takes place, which I have nothing to do with. And so to the vast majority of you who are not tempted to and have not used problem set solutions, I want to thank you because it helps me make this course the best course it can be. But I remind you that in general, I'm very easygoing and very nice about all sorts of things. But this is one thing that I take seriously, and if there are cases where I think that plagiarism has taken place, then I have no choice but to deal with it in the way that the university requires me to. Okay. So if you have any questions about this, you should feel free to contact me, email. You can always come to my office at some point. And hopefully we won't have to have any further discussions on this matter because I'd really much rather focus on the physics. Okay. So maybe I'm not going to ask if any of you have any questions on this right now because I think I've made my point of view pretty clear. If you have any things you'd like to discuss with me privately, of course I'm always available. Okay. Good. So let's go ahead and start with some physics. So last week we began developing the theory of the continuous symmetries of various systems in quantum mechanics. And in particular, we saw that the prototypical example of a system with continuous symmetries is a system which is rotationally invariant. So rotation symmetry, let me just remind you, is the statement that we have a system, say, in three-dimensional space, which is invariant under the 3x3 rotation matrices that rotate the three coordinate x, y, and z axes. And in terms of the geometry of three-dimensional space, these rotation matrices are orthogonal matrices, and they obey a particular group multiplication law. This group multiplication law is determined by the algebra of the generators of rotation. And because of this, the description of rotation symmetry in quantum mechanics will follow from a representation of the rotation group, which will act on the Hilbert space of your quantum mechanical system. So in particular, the Hilbert space of whatever quantum mechanical system you are hoping to describe must be a representation of the rotation group which is known as SO3, the group of 3x3 orthogonal matrices which have determinant 1. And the algebra of the infinitesimal generators of this rotation group obey what is known as the SO3 or SU2 algebra, which you have already encountered in your quantum classes, and we began to discuss last time. So, before diving into the general theory, let me just remind you of a very simple example of a system with rotation symmetry, which is that of a particle moving in 3 dimensions. So, the position and momentum operators are Hermitian operators that act on the Hilbert space of the particle, that is to say the wave functions, and the angular momentum operator, x cross p, is, when we think about it as a operator acting on the wave functions that are functions of 3-dimensional space, just given by a simple formula. So it's the cross product of x with minus I h bar times the gradient, or if you write that out in terms of the differential operators that represent the momentum operator, it's the cross product of x with d by dx. And I'm using here Einstein's summation notation, and the symbol where the epsilon symbol, epsilon ijk, is equal to plus or minus 1 if ij and k is an even or an odd permutation of 1, 2, 3, and is equal to 0 otherwise. Okay. So everyone here is familiar with that notation for the epsilon symbol? Okay. If you're not, I'm happy to come. So, for example, that last equation I wrote, is everyone happy with that equation? Okay. Yes?
What does it actually mean having the I up?
Oh, yeah, okay. I should be a little, I should make a comment on that. So sometimes we, yeah, okay. If you like, we could write it this way. For the purposes of this class, there's no difference between an index that's a superscript and an index that's a subscript. Okay. In other contexts, we often use subscripts and superscripts to denote something slightly different. A superscript denotes a vector, and a subscript denotes a contravariant vector. So for people like me who are general relativists by trade, it's sort of difficult for me to not keep track of the indices. Okay. So often you'll see me writing indices up or down depending on how they transform in some way that you don't particularly care about. Okay. So from your point of view, you can ignore the placement of the indices. But for those of you who have taken or will be taking general relativity, you could keep in mind that the placement, superscript or subscript, is usually used to denote a transformation property under coordinate transformations that is worth keeping track of. Okay. But for your point of view, don't worry about the superscripts and subscripts. It's just, for me, I find it sort of painful to write down an expression where they're, yeah, I find it morally repugnant. Yeah. For me personally, I find it difficult to write down expressions. It hurts me a little bit. I die a little bit inside every time I write down an expression where the indices are placed incorrectly. So, it's a personal quirk of mine. Yes. Good. Okay. And, of course, these generators are Hermitian operators that act on the Hilbert space of the particle moving in 3 dimensions, which obey the algebra, which says that the commutator of 2 of them is equal to a third. The commutator of L1 with L2 is equal to I h bar times L3, and so on and so forth. Okay. And as I mentioned last time, I could, of course, remove the h bar by using a normalization where the L's are dimensionless rather than have dimensions of angular momentum. But for the purposes of this class, it's a class in quantum mechanics, so we should always keep our h-bars around and keep everything dimension with the correct dimensions if we can, just to make the physics a little clearer. So I won't go ahead and renormalize these to get rid of that factor of h-bar. Okay. So this means that the Hilbert space of a particle in 3D is a representation of the rotation group. Remember, the word representation is just a fancy way of saying that there are Hermitian operators L1, L2, and L3 that act on this Hilbert space, which obey this rotation algebra. Okay, and the Hilbert space, of course, is just the set of square normalizable functions of x1, x2, and x3. Okay. And we give a name to this representation. We call this the orbital angular momentum representation. Orbital, I suppose, is for historical reasons because we're used to thinking about this in the example, say, of an electron, which is orbiting the nucleus of some atom, such as the hydrogen atom. But the question that we would like to ask today is what other Hilbert spaces can be acted on by these rotation generators? That is to say, for what other Hilbert spaces can we have a rotationally symmetric theory? Okay. So, in particular, what that means is that we seek a Hilbert space such that there are Hermitian operators Ji, which obey the rotation algebra Ji with Jj commutes to IH bar epsilon ijk times Jk. Okay. One word about notation. Typically, we use L to denote the rotation generator for the algebra of orbital angular momentum, so when acting on three-dimensional wave functions. And we use something like J or S to denote the action of the angular momentum Hermitian operators on some other Hilbert space. So, for example, what we're going to do now is we're going to work out the finite-dimensional Hilbert spaces which can be acted on by these rotation generators. These will represent particles with spin, and usually people will denote by L the orbital angular momentum, by S the spin part of angular momentum, and they might use a symbol like J for the total angular momentum. That's some notation that varies somewhat with different authors. I'm going to try and stick as closely as possible to the notation of your textbook. Okay. Now, before I begin, let me just pause and see if there are any questions. Good. So, the first thing that we do is we need to choose some element of this algebra which will be diagonal. Remember that one can always diagonalize a Hermitian operator such that the eigenvalues are purely real, but because these three rotation generators do not commute with one another, it's impossible to diagonalize them simultaneously. So we'll just need to go ahead and choose one of these generators and declare that to be the one that we're going to diagonalize. And the conventional choice is to have it be J3, the operator that generates rotations about the z-axis. Okay. And so a basis of states can be organized into eigenstates of the angular momentum operator J3. Okay. And let's look for a Hilbert space, that is to say, for a representation of dimension n, which is finite. Because the Hilbert space has a finite dimension, that means that there is a state which has the highest J3 eigenvalue. And let's call it the state J. And because the angular momentum operator has units of h bar, it's dimensionful, what I'll do is, instead of having the eigenvalue of that state J under J3 just be the number little j, it'll be the number little j times h bar. So that little j is going to be a dimensionless quantity rather than a dimensionful quantity. That's just some convention. Question?
When you say that we're looking for a definition of dimension n, doesn't the number of operators determine the dimension? Or
No. As we'll see, the number of operators will constrain the possible dimension, okay? But it doesn't uniquely specify the dimension. So, for example, it will turn out that for representations of the angular momentum algebra, it's possible to have any value of n, okay? Even with 3 elements. If you're bored, think for yourself and try and figure out what that representation is before I get to it in 1 page and a half. Okay. But I should mention that there are other sorts of more complicated symmetries where that is not true and the dimension can be arbitrary. So, for example, one of the simplest generalizations of the rotation group is the group of symmetries of the quarks in nature. And in that case, n has to be either 1, 3, 8, or something like that. And it's that constraints which lead to the organization of the fundamental particles into groups of 1, 3, 8, and so forth. That was first observed by Gelman, and which is why he's such a famous guy. Okay. If you don't understand that, don't worry. It's going to be on your next problem set. I think. Actually, it was last year. I might tweak it because, yeah. We'll see. Okay. Okay. So, in particular, let me just assume that there's a unique state with highest eigenvalue. Okay. It might not be unique, but let's just assume that it is. It'll become clear in a little bit what will happen if it's not a unique state. So let's assume that there's a unique state with highest J3 eigenvalue. And rather than working in terms of J1 and J2, let's denote by J plus and minus the following linear combination of J1 and J2. So J1 plus I J2. So these operators are no longer Hermitian, but rather they're going to be Hermitian conjugates of one another. I'm sorry that what I mean by my symbol for adjoint is very similar to my symbol for my plus. Okay. But this equation here is supposed to say that the adjoint of J minus, the Hermitian conjugate of J minus, is equal to J plus. As you can see, because of the addition of that I there in J1 plus I J2. And then it's easy to check that in terms of J3, J plus, and J minus, the rotation algebra takes the following form. That the commutator of J3 with J plus and J minus is just plus or minus J plus or J minus, and the commutator of J plus with J minus is proportional to J3. And those H bars have to be there just by dimensional analysis. Okay. And it's a completely straightforward exercise, which you've probably seen before, frankly, to write out the rotation algebra in this form. Okay. Now, I would like to bring your attention to this first formula. Okay. So what do we have here? We have an operator J3 such that its commutator with J plus is equal to J plus, and the commutator with J minus is equal to minus J minus. And I want you to think back to something that we did several weeks ago in this class, which was the algebraic construction of the Hilbert space of a harmonic oscillator. For the harmonic oscillator, we had raising and lowering operators A and A dagger, which were adjoints of one another, and they had the property that the commutator of the number operator with A was equal to minus A, and the commutator of the number operator with A dagger was equal to plus A dagger. So if you look at this expression here, what you'll see is that that is the identical expression, just with J3 playing the role of the number operator, and J plus and J minus playing the role of the raising and lowering operators, A and A dagger. So that immediately tells us how we can go about constructing the Hilbert space, which is acted on by these rotation generators. Okay. So in particular, if you have some basis state, which is an eigenvalue of J3 with, which is an eigenstate of J3 with eigenvalue H bar times M, then you could act on that state with either J plus or J minus. And then, using the rotation algebra, we could ask what happens if you took that state and acted on it with J3. So if you act on it with J3, well, just using this equation here, you can easily see that you get back exactly the same state, except that its eigenvalue has been shifted by a constant. So that J plus or minus, acting on a state with m units of angular momentum, will give you a state which has m plus or minus 1 units of angular momentum. J plus and minus will either raise or lower the eigenvalue of J3 by exactly 1 unit. Okay. So, for example, this implies that if you take the state J, which I introduced up above, which I remind you is the state with the highest amount of J3 with the largest J3 eigenvalue in your Hilbert space, and you act on it with J plus, well, that should give you a state with 1 higher unit of J3 angular momentum. But we already assumed that J was the state with the largest angular momentum, J3, in your Hilbert space, which means that that constant appearing here must be equal to 0. In other words, if the state J is the one with the largest J3 eigenvalue, then when you act on it with the operator J plus, that increases the amount, the J3 eigenvalue, you have to get 0. Okay. And this is the defining equation for that state J. Exactly as in the harmonic oscillator, the ground state was defined by the equation that it was annihilated by the lowering operator. A acting on the ground state was equal to 0. And if you act on the state with J minus, you'll get a constant times a state with 1 less unit of angular momentum. So you'll get a constant that I've called Cj times the state J minus 1, the eigenvalue of J3 with the eigenstate of J3 with eigenvalue H bar times J minus 1. And this constant Cj can be computed just by using the fact that all of our states should be unit normalized. So for example, if you take the norm of both sides of this equation, and you demand that the state J minus 1 has unit norm, then that implies that Cj squared is equal to, well, the norm of the state J minus acting on J, which, if you just go up and you look at at this second expression, is going to be equal to 2 H bar times squared times j. Just because you can commute j plus with j minus, and j minus j plus acting on j is 0 because j plus annihilates the state j when acting from the left. And you're left with just 2 h bar times the j3 eigenvalue, which is, of course, h bar j, for a total result of 2 h bar squared times j. Okay. And one can then proceed further to, for example, act with j minus on the state j minus 1 to get the state j minus 2, and so on and so forth. And in general, the result is that if you take j minus and you act it on a state j minus k, you'll get some constant of normalization, which is just easy to work out using the rotation algebra. So it's just that constant I've written there, h bar, by dimensional analysis, times the square root of k plus 1 times 2j minus k. Okay. So what do we have? So we start with the state j and construct the states j minus to the kth power acting on j, which are proportional to the states j minus k. And the only difference between this construction and the construction of the Hilbert space of a harmonic oscillator came from this expression right here. So remember that for the harmonic, so j plus and j minus are playing the roles of the raising and lowering operators. The commutators of the raising and lowering operators for the harmonic oscillator was equal to 1, but the commutator of j plus and j minus is not equal to 1, it's equal to j3. Okay. So that means that although the construction was very similar to the harmonic oscillator, it led to this normalization constant here that is actually slightly different. And in particular, to have n states in our Hilbert space, this constant out front of this normalization, so that constant, the square root of k plus 1 times 2j minus k, must vanish when k is equal to n. Because otherwise we've constructed too many states in our Hilbert space. That means that j must be equal to n over 2. So what have we proven here? We've proven that in quantum mechanics, angular momentum is quantized in units of h bar over 2. Okay. Thus, in quantum mechanics, the j3 eigenvalues are quantized, and in particular, they must take half-integer values. So j3 acting on some state has to be h bar times an integer over 2 acting on that state, at least if it's a j3 eigenstate. Okay. So you can see then that simply the presence of rotation symmetry automatically guarantees all sorts of very interesting information about the possible values that the angular momenta can take in quantum mechanics. Okay, now just a little bit of notation. So states in this Hilbert space are usually written as follows. So a state in this Hilbert space is usually written as with two variables. So where M is the J3 eigenvalue, I should really be putting my superscripts and subscripts consistently, and J is the highest J3 eigenvalue in the Hilbert space. Okay. So for a given state, M is the J3 eigenvalue, and J is the highest J3 eigenvalue that you could find in this space. Okay. So that, for example, J3 acting on this state will be an integer, or will be some number M times H bar acting on the state. And M will take values that run between minus J and plus J. And J will be a half integer. So in particular, what we see is that the possible representations that we could have, the possible Hilbert spaces that we could have, are constrained in this way. Now, last class, when I was studying the theory of continuous symmetries in some generality, I introduced the notion of a Casimir of an algebra. And the Casimir of the rotation algebra is, in fact, the operator J squared. What does it mean for it to be a Casimir? That's just the statement that it commutes with all of the rotation operators. And so one could also use the Casimir to label the different Hilbert spaces. Okay. Instead of using I've used little j to denote the highest J3 eigenvalue in this Hilbert space. But I could also use the Casimir J squared to label the Hilbert space. And indeed, one can check. So this is easy enough to derive. You could just compute J squared for this space. And you would find that it's J times J plus 1 times H bar. Okay. That's a straightforward computation. Okay. Have you guys done that before? I'll assume that you've done that before. Okay. And then it's easy enough to work out the matrix elements. So that, for example, if you have this Hilbert space, this again is essentially, I'm just rewriting a formula that I derived for you a few minutes ago. The matrix element of the operator J plus I'm just going to write out the answer for you, is equal to some integer times H bar times a delta function which sets M prime equal to M plus or minus 1. Okay. That is to say, J3 is a diagonal matrix, and J plus and minus, so J plus has entries just above the diagonal, and J minus has entries just below the diagonal. Just one more piece of semantics or notation here. So we refer to the Hilbert space spanned by these guys for some fixed J as M runs from J minus J all the way up to plus J as the irreducible representation n of the rotation group, or as the spin n over 2 representation of the rotation group. So we label these different representations just by that integer n. Okay. So if I talk to you about the irreducible representation 1 of the rotation group, then that's a very simple irreducible representation. It's the one-dimensional Hilbert space where all of the j's are just given by 0. Okay. So the rotations don't act on them at all. So for example, the n equals 2 representation, i.e. the spin 1/2 representation, is a little more interesting. So this is a representation that you all know and love, hopefully. It's the representation where these j's are just h bar over 2 times the Pauli matrices sigma I. Okay. So sigma 1 is 0, 1, 1, 0. Sigma 2 is 0I minus I0. Sigma 3 is 1 minus 1 with zeros off diagonal. And you can see from this expression, for example, that J plus is proportional to sigma 1 plus I times sigma 2. That's the matrix 0, 1, 0, 0. So indeed, it has its only non-zero entry just above the diagonal. And likewise, sigma minus has its only non-zero entry just below the diagonal. And these Pauli matrices obey all sorts of wonderful properties that I'm sure you all know and love. For example, they square to 1. They are Hermitian. They all have determinant -1, and they are all traceless. And their algebra can be succinctly summarized by writing down their commutators, which of course is given by the usual rotation algebra, without the h bar there and with a different factor of 2, just because of that conventional normalization of h bar over 2 there, along with this expression for their anti-commutators. Okay. So their anti-commutator is just delta ij, okay, or twice delta ij. Actually, let me just, as an aside, make one additional comment. Okay. So the algebra of these Pauli matrices is sometimes called the quaternion algebra. I bring this up not because I want to tell you anything specific about quaternions, because there's nothing I could possibly tell you about quaternions that I haven't already told you just in the language of Pauli matrices. But I bring it up because you'll very often hear, or not very often, it depends on what circles you run in and what kind of friends you have, but sometimes you will hear people talk about quaternions. So just as the real numbers can be generalized to make complex numbers, provided you allow the numbers to square to -1, the complex numbers can be generalized to form a set of numbers known as the quaternions, provided you allow the numbers to not commute with one another anymore. Okay. And in fact, the algebra of quaternions is nothing more and nothing less than the algebra of Pauli matrices. So anytime anyone tries to intimidate you by talking about the quaternions, you should not feel intimidated because you already know the Pauli matrices. And all the quaternions are is a different way of writing down 2x2 matrices, okay, and organizing them in terms of the Pauli matrices. Have you guys seen quaternions before? You haven't. You have. You may have. You may have run across them. But one of the things that you may not have been told is that they're nothing more and nothing less than Pauli matrices. Let's now ask then about the more complicated representations. So let me just give you one more example. So the n equals 3, that is to say the spin 1 representation, is the representation where J3, so that has eigenvalues 1, 0, or minus 1. So it'll be that diagonal matrix. J1, well, I'm just going to write out in more detail the formulas that I wrote for you earlier. So that's J1. Here's J2. So I'm not doing anything sophisticated except writing out the forms of these matrices so that you can stare at them for a minute. So what is the deal about this spin 1 representation? Well, this is the representation where J3 takes values 1, 0, or minus 1. J plus and J minus now look like the matrices which either have 1s on the diagonal just above the diagonal, the 45-degree line just above the diagonal, and J minus has entries just below the diagonal. Question?
Earlier, weren't you saying that the highest value of J has to be n over 2?
Yeah, sorry. What? I might have made an incorrect statement up above. Okay. The highest so it's n plus 1 over 2. I did my counting wrong. You're right. So where was that mistake? Or is it n minus 1 over 2? It's n minus 1 over 2. Yeah. Where did I... the spin n minus 1 over 2. I'm sorry about that. Right? Because the one-dimensional representation has spin 0. Okay. So there's an n minus 1 over 2. I'm sorry about that. You're right. Okay. Where did I made that mistake somewhere else. Okay. There it is. So J is equal to n minus 1 over 2. Right? Okay, thank you for that. Because if you act with you see what I'm saying? Okay, good. Any questions on that? I apologize. Okay. Good. Okay. Any other questions so far? So of course you guys have seen Pauli matrices before. Have you seen the spin 1 representation before? Okay, good. Well, now you've seen it again. Okay. Yes? Jx and Jy. Yeah. The rotation generator about the x-axis and about the y-axis. Okay. So, for example, J1 is the thing that for orbital angular momentum would be represented by y d by dz minus z d by dy, or y p z minus z py. Okay. Good question? Other questions? Yeah. I sort of use x1, x2, and x3 interchangeably with x, y, and z. Yes?
When we derived this, why did we start with 3 operators? Was it just only by analogy with values?
Why did we start? Well, why did we start with 3 algebras, 3 operators? The rotation, remember that a rotation is described by 3 angles. Okay. That's the statement that the rotation group is 3-dimensional.
Even in 2 dimensions?
No, okay. We're talking about rotations in 3 spatial dimensions. For example, if you were a materials physicist studying electrons confined to the plane, as many materials physicists would do, then you would be interested in rotations in 2 dimensions. There's only one rotation in 2 dimensions, okay, which is the rotation about the axis perpendicular to the plane that your electrons are in. So in that case, the representations are much simpler. They're just given by one number, which is the eigenvalue of your states under that rotation generator. There's nothing too much that I can say about this that we haven't already said. Okay. In higher dimensions, life, of course, would get much more interesting. So, for example, If we had a particle moving in 4 dimensions, then you would have an SO4 rotation symmetry, which is a 6-dimensional group. Okay. Now, particles moving in 4 dimensions are not particularly interesting to us as physicists living in 3 dimensions. But in special relativity, you learned that space and time are treated on equal footing. Okay. So that means that if you study theories of quantum mechanics, which are invariant under special relativity, which are invariant under the Lorentz transformations of special relativity, then that is essentially exactly what you're doing. And it's exactly what we will do next class. Okay. We'll be studying the representations under these fancier, more complicated groups, those relevant for the symmetries of special relativity. Okay. In fact, as we'll see, we've already worked out all of the mathematics. Okay. All of the theory the theory actually reduces completely to the theory that I've already worked out for you this class. Okay. We just have to understand how to apply it correctly. Okay. So the number of generators depends on what symmetries you're thinking about. Let me give you another example, an example that I do think is on your problem set next class. Let's consider the case where you have 3 harmonic oscillators with the same frequency. Okay. In that case, it turns out that there's a different set of symmetries known as SU3, and there are 8 of those, okay, rather than 6 for SO4 or the Lorentz group, or 3 for the rotation group. And so that, in fact, is a totally different theory of symmetries. And it's a theory that is very useful for understanding, for example, how the states of the hydrogen atom are organized, and also for how the states of quarks and the various elementary particles are organized. So depending on what sort of system you're studying, you'll end up with different kinds of rotation groups, different kinds of symmetry groups. Are there any other questions? This is a great time to pause and ask questions. All right. Okay. So far, we have worked out the expressions for these generators J, which give us the infinitesimal rotations, and finite rotations for a given representation are found by exponentiating these infinitesimal rotation generators. So, for example, if you want to describe a rotation, say a rotation by an angle phi about some axis theta hat, here, let me write it, then the corresponding rotation generator, r of phi theta hat, is just the exponential of minus I over h bar times the vec times phi theta hat dot j. To understand that expression, just consider the case where you're doing a rotation about the z-axis by some angle theta. Then you would have e to the I minus I over h bar theta times j3. Okay. And remember that the definition of these angular momentum guys is that they're the things that you get when you Taylor expand r for small angles theta. In other words, one can construct the full unitary operators r that describe these rotations by exponentiating the Hermitian operators j that give you the infinitesimal rotations. So, for example, on the spin 1/2 Hilbert space, the operator, the unitary operator that just gives you a rotation by an angle phi about the theta hat axis is just found by exponentiating those 2 by 2 Pauli matrices that we worked out earlier. And in fact, it's quite easy to write down using the algebra of Pauli matrices. It's just given by the following expression. Okay. Have you guys derived this expression before? It's a great little exercise. The way that you derive it is you use the fact that the exponential is defined by a Taylor expansion in powers of the argument of the exponential. And then you just go ahead and you use these relations down here an infinite number of times. Okay. Or another way of deriving it is by using the Campbell-Baker-Hausdorff formula. Okay. Those are both two different equivalent ways of deriving this expression. And roughly speaking, the cosine and the sine arise because cosine and sine are the things that you get if you keep either the even terms or the odd terms in the Taylor expansion of an exponential. Okay. So, for example, this formula should look very similar, for example, to the formula that e to the I phi is equal to cosine phi plus I sine phi. It's just a mild generalization of it when we're exponentiating 2 by 2 matrices instead of just numbers. Question? Oh, no, you were just scratching your face. Okay, proceed. Okay. Let's write this out a little bit more explicitly. So if you just use the expression for the Pauli matrices that I wrote down for you earlier, what is that? Well, along the diagonal, you have a cosine phi over 2 from the first term minus I times the component of theta hat in the z direction times sine phi over 2. Okay. And then on the lower diagonal, you'll have exactly the same thing, except with a plus I. And then on the off diagonals, you get the contributions from sigma x and sigma y, which had off diagonal elements. So what are they? You get minus I, theta x hat, minus theta y hat, times sine phi over 2. And then you have the complex conjugate of that down here. Okay. So this is just some explicit 2 by 2 matrix, which acts on the Hilbert space of a spin 1/2 particle that gives you an arbitrary rotation. Okay. So there are a few comments that I would like to make about this expression. The first thing that I would like to note is that if you evaluate this, when phi is equal to 2 pi, for an arbitrary axis, axis of rotation theta hat, what do you get? Well, you get minus 1. The sines are all equal to 0, but you get cosine not of phi, but cosine of phi over 2. Cosine of pi is minus 1. What does this mean? This means that under a 2 pi rotation, a spin 1/2 particle has its state transforming not back to itself, but only back to itself up to a minus sign. So this is a very curious fact. Okay. Usually, if you take something and you rotate it by 2 pi, it comes back to itself. But we're seeing that spin 1/2 particles, and indeed any sort of particle with half integer spin in quantum mechanics, does not have this property. It only comes back to itself up to a minus sign. So, in fact, there are some very interesting ways of understanding exactly why this is true. So to understand this a little bit more explicitly, let's consider this Hilbert space of a spin 1/2 particle. And let's write out a state in this Hilbert space. Just in two-component vector notation. So that we have a state psi, which will be, let's call it, psi plus times the state with j equals 1/2 and m equals 1/2, plus psi minus times the state where j is equal to 1/2 and where the total angular momentum, of course, is still 1/2, but where m, the j3 eigenvalue, is minus 1/2. And then the states are two-component vectors, which can be represented by a column vector, and such two-component column vectors, which are acted on by these rotation generators, are referred to as spinners. In the same way that a vector is the three-component thing that is acted on by a rotation generator, a 3x3 rotation matrix, a spinner is the two-component complex column vector, which is acted on by one of the rotation generators that I wrote down in terms of Pauli matrices. And the important point is that these rotation generators act by unitary 2x2 matrices with determinant which preserve the norm of the state, so psi plus squared plus psi minus squared. Okay, that's just what a unitary operator does for a living, and have determinant equals to 1. Okay. In general, a 2x2 unitary matrix need not have determinant equal to 1. It could have determinant equal to some phase, like I or minus 1 or something like that. To see that they have determinant 1, just go up to that 2x2 matrix that I wrote down for you above, take its determinant, work it out, and you'll see that it has determinant 1, precisely because its determinant will be the length of the vector theta hat. Okay. In particular, let's stare at that expression for a second. Okay. So what is the determinant? Well, you get a cosine from the product of the diagonal terms. You get a cosine squared phi over 2 minus sine squared or plus sine squared phi over 2 times theta z hat. From the product of the two off diagonals, you'll get a plus sine squared phi over 2 times theta x hat squared plus theta y hat squared, using the fact that theta hat has unit length and that cosine squared plus sine squared is equal to 1, you'll see that this matrix then has determinant 1. Okay. And the set of all possible rotation matrices act as unitary operators acting on this 2x2 Hilbert, this acting as 2x2 transformations, is the set of all unitary matrices with unit determinant. This set has a name, just as I called SO3 the set of all 3x3 orthogonal rotation matrices. This is known as SU2. U stands for unitary, S stands for special, which means the determinant is equal to 1, and 2 stands for 2x2. And in fact, as you might guess, based on what we have seen so far, the group SO3 and the group SU2 are in fact very closely related. Okay. In particular, the algebra of generators of the rotation group SO3 is equal to the algebra of generators of SU2. Indeed, we constructed SU2 by looking at the algebra of generators of SO3 and then exponentiating them. So you know that that's true. So that means that a local rotation is the same as a local SU2 transformation. But the global properties of these spaces are not the same. So globally, as groups of symmetries, actually, these groups differ. In particular, in terms of the usual rotations of three-dimensional space, each angle phi between 0 and 2 pi and unit vector theta hat give a unique element, or rather I should say it slightly differently. Each element of SO3 is uniquely specified by an axis about which you rotate theta hat and an angle phi between 0 and 2 pi. Okay. Whereas each element of SU2 is uniquely specified by an axis theta hat and an angle phi which runs between not 0 and 2 pi, but 0 and 4 pi. Because if you rotate by an angle 2 pi, your state of a spin 1/2 particle picked up a minus sign, so you need to rotate by an angle 4 pi to get back to the original state that you started with. So mathematically, we say that SU2 is the twofold cover of SO3. Okay. That's just a very fancy mathematical way of saying that for each angle phi between 0 and 4 pi that we use to specify elements of SU2, there are actually two SU2 matrices that give you the same rotation when you think about it as a rotation in SO3. But just to say that again, slightly differently, for each rotation in SO3 by an angle 2 pi, there are actually two possible ways that it could act on spinners. If you think about the rotation that does nothing as rotations in a three-dimensional space, that could either be a rotation by an angle 0 or a rotation by an angle 2 pi. Those both do nothing in terms of three-dimensional space, but they do different things in terms of their action on spin 1/2 particles. So the question then is, which of these is the rotation group used by nature? And it turns out that in symmetry, in nature, rotation symmetries are not SO3 elements. Nature instead uses SU2. That is an experimental fact. And for the purposes of this class, we will just have to take it as an experimental fact. Although, in a class on relativistic quantum mechanics or quantum field theory, one could, in principle, derive it. Actually, we could probably derive it in this class if we wanted to. It follows from the fact that the rotation group SO3 has topology, whereas the rotation group SU2 does not have topology. So that will get into a bit more of a mathematical discussion than I think is appropriate for this course. But if one so one of the things that one might do in order to understand the possible allowed representations of a group of symmetry is consider the topology of the group of symmetries. If you don't know what topology is, don't worry, because this is one of the last times I'm going to mention it in this course. But just to say that there are ways of understanding this using somewhat, I would say, more highfalutin, but not necessarily more complicated techniques. Okay. Are there any questions? You're presumably already familiar with the fact that spin 1/2 particles pick up a minus sign when you do a 2 pi rotation. But you may not have seen the derivation of it, or if you have, you may not remember it. So I think it was important to go through. Questions? Comments? Feelings? Thoughts? What's that? The assignments are too long? Okay. The assignments are actually shorter than they were in previous years, believe it or not. The last one was too long? Okay. Okay. Well, let's not... Are there any feelings about rotation symmetries, which is thoughts about rotation symmetries that you wanted to share with the group? I wasn't actually asking... Okay, I suppose I walked right into it. But yeah. Okay, good. Okay. Let me now tell you about a few more interesting features of the algebra of rotation symmetries. Okay. Yes?
So if I take a spin 1/2 particle and I flip it around one time,
yes.
It will have the negative state, but I can't really see it because
Good. That's an important point. Okay. In quantum mechanics, 2 states that are related by an overall multiplication by a constant are physically the same state. Okay. So you might think that this is unobservable. But remember that we can measure that constant if you consider interference between 2 different states. Okay. So for example, you could take 2 states and perform some interference experiment. Okay. Then you could take 2 states and rotate one of them by 2 pi and perform the same interference experiment. You actually could observe things like this phase. Okay. So, for example, if you study interference between electrons or something like that, this is important. Good question, though. Yes. What's that?
How do you rotate it?
You pick it up and you rotate it by 2 pi. I mean, an electron is a particle, okay? What is a particle? It's something that you could pick up and manipulate. Maybe you can't pick it up with your hands, but you could manipulate it using electric or magnetic fields or something like that. Yeah. So this is something that's actually true, okay? I'm not just pulling your leg here. This is something that's actually true about electrons. Are there other questions? Okay. So here's a little fact. And this is not something that I'm going to prove to you, but it actually is relatively easy to prove. Okay. Which is that every Hilbert space which is a representation of the rotation group is a direct sum of these finite dimensional irreducible representations. So, in particular, if we let H sub n be that Hilbert space that I described above, which is the irreducible representation of dimension n, then a general Hilbert space, which is acted on by the rotation group, will be some direct sum of the form Hn1, Hn2, and so on and so forth. Okay. And it might be either a finite or an infinite direct sum, depending on whether your Hilbert space is finite or infinite dimensional. And here, I use the symbol of a plus in a circle to denote the direct or Cartesian sum. And it's important to remember that this is not the tensor product. Okay. Rather, it's the direct sum that I introduced for you a few weeks ago when we discussed the theory of entanglement, which is defined, I remind you, as follows. So that if you have some Hilbert space, H1, with some basis, and another Hilbert space, H2, with a different basis. So here, let's say that I runs from 1 up to n1, and j runs from 1 up to n2. Then the direct sum is the Hilbert space whose basis is just the union of the two. The set of all psi i's and chi j's. And it has dimension which is the sum of the dimension of H1 and the dimension of H2. And the operators on H1 and on H1 plus H2 are block diagonal matrices. Okay. So the direct sum is more naturally what you think of when you think of combining two vector spaces to make another. Okay. So for example, the vector space of vectors in 3 dimensions is the direct sum of 3 one-dimensional vector spaces. Okay. And this fact that any representation of the rotation group is a direct sum of the irreducible representations, so this formula here, is just a fact about the theory of groups that's actually not hard to prove, but I'm just not going to bother to prove it to you here because this is really a physics class rather than a math class. Indeed, the fact that H is a sum of these representations is why I use the word irreducible when I describe the spin J representation as an irreducible representation. So if you think about the theory of Hilbert spaces as analogous to the theory of numbers, then the irreducible representations play the role of prime numbers. And just as every number is a product of prime numbers in a unique way, every Hilbert space, which is acted on by the rotation generators, is a sum of these irreducible representations in a unique way. Okay. So let's consider an example. So let's take 2 particles of spin S1 and S2. Okay. Then that means that the Hilbert space is the tensor product of the spin 1 representation and the spin 2 representation. And it has let me not mix my notations up. Let me call it H sub n1 times H sub n2, where n1 is 2s1 plus 1, and n2 is 2s2 S2 plus 1. Okay? And this Hilbert space has n1 times n2 elements. So it has dimension n1 times n2. Okay. And we know that if you have two particles with spin, then that must be acted on by the rotation generators in some way. So it must be possible to write out this tensor product Hilbert space in terms of a bunch of direct sums, which are these irreducible representations. Okay. And indeed, there is a simple way to do so. I'm not going to actually prove it to you, but rather I'm just going to work it out in a couple of simple examples so that you can see how it works. But the general answer is that the tensor product, here, how should I write this? The tensor product of these Hilbert spaces is actually the sum of a bunch of different Hilbert spaces. So there's the Hilbert space, let's call it, with dimension 2, S1 minus S2 plus 1, plus the Hilbert space with dimension 2 times S1 minus S2 plus 1 plus 1, added together all the way up to the Hilbert space with dimension 2 S1 plus S2 plus 1. Okay. i.e., or in other words, the sum of all possible spins running between S1 minus S2 and S1 plus S2. And I should make one caveat, okay, which is that I've actually assumed here that S1 is greater than or equal to S2. Okay. If S1 is less than S2, then you actually have to interchange S1 and S2 in this expression. Okay. And, well, therefore, one could prove this formally, but instead I'm just going to work it out in some examples. But the way that one should understand this is just by noticing that, among other things, this formula requires that the dimension of the Hilbert space on the left-hand side has to be equal to the dimension of the Hilbert space on the right-hand side. And that's just the formula. That's just some simple formula that is easy enough to prove. Okay, something like that. So very often, if you want to work out one of these rules, one of the quick and dirty ways of working it out is just seeing how the dimensions could possibly add up to make it work out. And in fact, this is an expression that I'm sure you have seen before, because you've even seen it in problem sets that you've done in this class before. Because this is just a statement that if you take two spin 1/2 particles and consider the combined system with both of them, then there's one spin 0 state that you can form out of it and 3 spin 1 states that you could form out of it. So that, for example, the product of the two spin 1/2 Hilbert spaces is just the sum of the singlet Hilbert space, i.e. the one with the spin 0 and the spin 1 Hilbert space. And indeed, as we'll do next time, because I'm running out of time here in class, one can work this out completely explicitly in that case. And it's illuminating, I think, to do so. And in doing so, one encounters what's known as the theory of Clebsch-Gordon coefficients. Frankly, I find Clebsch-Gordon coefficients incredibly tedious, and in the days of Mathematica and Maple, I don't think it's really necessary to spend too much time dwelling on them, for which you should be thankful. But maybe I should stop here and see if there are any questions. Maybe I'll ask a question for you. Do you really think the problem sets are too long? Okay. They actually, believe it or not, they're easier than they're short. I've been removing problems relative to last year. Okay, believe it or not. How many hours are you spending on the problem sets? 8. That's fine. Okay. I think that between 5 and 10 is fine for a course like this.
5 and 10 days.
Oh, you said days? Okay. I mean, part of my philosophy about this course is that there's no exams in this course. Okay. And one of the one of the trade-offs that we have for having no real exams in this course, only having one take-home exam, which is just a problem set, basically, is that the problem sets are more difficult. So, I mean, it's a trade-off, okay? Because, I mean, do you feel that the problems are interesting? Do you feel that you're learning? Okay, that's all I care about, really. And, my point of view is that I think that people learn. I don't like exams, okay? I think they're bullshit. I don't think you learn very much. And I think what you do learn, you quickly forget. And so I would much rather have problem sets in a take-home than a final. But the trade-off is that I really have to make sure that you learn a lot, okay? And the way that I do that is by having long but interesting problem sets, okay? So how many hours do you feel like you spend on? How many people feel like they spend more than 10 hours on a problem set? Okay, most people. How many people feel like they spend more than 15 hours? And how many people are lying when they say that? Because everyone overestimates the amount of time that you work. Everyone says, oh, I work 80 hours a week. Nobody works 80 hours a week. Okay. Okay. Well, this next problem set is actually a little shorter. Okay. The next couple of problem sets are actually going to be a little shorter, I think. Let me think. Yeah, the first problem set's easy. This is a pretty easy problem set. This one's going to be shorter. I promise. Yeah. This one's going to be shorter. Okay. Okay. Well, your comments are noted and appreciated, and maybe I'll remove 1 or 2 problem sets on the subsequent ones. Okay. But the problem